hope to to finish what I first planned to. Then tomorrow I'm going to give slides. Tell you more about the geometry and the equivalence problem for single CR manifold, as well as the geometry and the dynamics associated with it. So now let's begin with let's recall what we did last time. So we have a manifold M, so strong pseudo-column X. So we want to normalize it. We want to find the best the best. So the best defining function we could.
What is the dimension of M?
Dimension M. So now it's hypersurface is and but when I talk about the more wire tensor, it's going to be at least 3 dimensions. Okay. So we mentioned that we mentioned that there is a normalization operator, so we have to be very careful. So we have to use this is FG equals to imaginary part G minus 2I, so Z bar means F, and the restrict with Heisenberg. So and here we assume FG equal to 0 at the origin, and meanwhile so F satisfy the minimum normalization. So so here what I'm saying, what we need is that so BT is spelled down. In this setting, we need this normalization condition. So so now we mentioned that so the range of this space, if some polynomial fit in the range of this space, we can eliminate. So we want to see so what would be the complement of the range. So now let's give a definition. Then I'm going to say the model theory. Okay. So the definition, so we let's say AS, and we mentioned that there is no third order invariance. Third order invariance equal to 0. So we start with let AS be a collection of real value. So polynomial of weighted degree S, of weighted degree S equal to 4 at least. So we let's say this A is the direct sum of AS. So first, let's say first we say A. So A is a set of unities. So a set of unities for the normalization operator. So if this solution for any G inside A, if this may not have a solution. If there is a solution, has at most one solution. If there is solution, this cannot be, so may not be a linear subspace. So we do not talk about homogeneous. It's not enough. Okay. So this is the first part. The second part says. So the second part says, so we say A, so admissible. I think I'm confused this for the LL operator. So if so the range of in respect to degree S plus AS, so this should be the whole space. Function polynomials of degree weighted degree S. So this means essentially for any element here, you can only find someone here so that is solved. So this means as so let me see here, any set of uniques for L. This has the most one solution. I think probably this is not needed. We mentioned that it's unique. Yeah. I think this is
last time you mentioned that
yeah.
of L.
Yeah, this is the result of the unique solution.
Yeah. So is it?
Yeah. So yeah. So that is right. So let's just give this, remove these things. So this is the only things we have. And so in my notes, actually our error is more general, so that's why. So now let's give a so by what we did before, now we have to follow the theorem. The theorem says, oh no, so I think I made a mistake here. So this is A, F, and G.
Is this A the set of what?
The set of uniqueness for the operator L. If the linear, so for any G in A, there's a unique, there's at most one solution. It may not be solved, but if there's a solution, but this is always one solution, right?
Yeah, because the kernel.
Yeah, the kernel is trivial, yeah. But for this one, let's drop this one. Okay. So for the most, I think then.
What is the theorem? You explain that.
No. So I'm sorry. Here, so actually, so we don't have this. We don't have this property here. So because of so in my normal form with Peter and Hema actually, so we want this uniqueness somehow. So we try the normalization. Then there may be a lot solution. Okay. So this is why. Okay. So this is why. So now so there's one more definition. So there's one more definition. The one more definition says so A is called a normal space. A normal space if both A and B holds. Both A and B holds. Okay. So now let's give a theorem. So the theorem says. So the theorem says essentially, the theorem says suppose A, so here, no space. Let's suppose A and B holds. I think I'm confused here. So A is a set of uniqueness for L, if L G good. I think we still need this normalization, otherwise, so. Let's forget about it. Let's do this. Just do this. And the origin will be 0. Okay. Yeah. But this A seems so I tell you a little later. Okay. So this holds or seems holds automatically. Okay. There must be something wrong here. So. Now we suppose A is a normal space. So for the normalization operator L. So then for any hypersurface of strong signal complex, and so there exists a unique. So by a formal holomorphic transformation. Formal holomorphic transformation. So formal holomorphic transformation. There exists a unique formal holomorphic transformation F. So but in this group, hypermorphic group. So this is normalized at the origin CF. Only this space. So which transforms? So which transforms M into a unique normal form. So a unique formal hypersurface. Formal hypersurface defined by V equal to norm D squared. So this is L. And so with A inside A. Okay, so that's so this is the property. Okay, that's what we proved before. So now There's some questions. There's some problem here. Okay. First, we only restrict the classification in a smaller group. This is the first part. The second part is that so we do not know yet. So this transformation is isomorphic. We are not classifying things in the formal category, in the isomorphic category. So there are two things. When you try to find this n, a, so now at a, you want to make sure at least so the transformation determines the class it lies to. Okay, and this is essentially this is essentially what given by Chambozo. Okay. One multiplied by Chambozo. So they're essentially there are now only two used for normal space. So this one is by Chambozo, the other one actually appeared. We found another one, but it's not linear one. So it's not linear one. So it's in my paper with Peter Epperfeld and Dimazaitis. So 2005. So American Journal of Math. So in my Chima lecture notes, I discuss more about the normal form here. Now let's just focus on the basic stuff. So the Chambozo theory part. Okay. So we have a non-normal form. We have non-normal space. So this is linear. This is non-linear. But this one is very convenient to use because essentially it's something people's problem. But however, we do not know the convergence here. But this one we know the convergence. But I'm going to tell you, but there is also disadvantage for this one. So now let's give a theorem due to Chambozo. So the Chambozo says, so before I say Chambozo, let's define the Chambozo normal space. So so that's NCH is a collection of these kind of polynomials. FKL bar, Z bar, U. So FKL bar equal to alpha bigger than equal to 2, delta bigger than equal to 2 and A alpha delta bar U. And Z alpha, V bar delta. All these are real values. We assume that they are real values. Assume they are real values. And here there is a trace condition. It's very important to pose this. So Laplacian scale, 2, 3 bar, and Laplacian cube. That's 3 bar. You assume this condition. Okay? So you assume this condition. So this condition, this is one of the most important one. And then so the theorem by Chambozo. The theorem by Chambozo. So first, so NCH is a normal space. And the second, most importantly, so this is the part they spend a lot of time to prove. Okay, for any real analytic, and here now real analytic M. For any real analytic M, so there exists a unique. Not unique, but there exists a bipolymorphic transformation. Bipolymorphic transformation. So F, such that, so the image of N is defined by equation V equal to normal scale plus N. And this N is in NCH. So in some sense, now, so this is the Chambozo theory, okay? So in some sense, so this sounds, now, so let's give some remarks. So what does this mean? So how is it related to the equivalence problem, okay? So the first part says, it's very convenient here, so the convenience, this is the, so this is the linear space. A linear subspace. So this is making it very convenient to apply. So what I'm saying, okay, now you start from 1M. For example, you start from 1M. So you start from 1M. Well, so you might have different normalization. So you might have F1 normalization, normal 1. You might have another normalization, F normal 2. Okay. So now, it's very likely. So this n normal 1 is not the same as n normal 2. So the defined function is the same, but they're still equivalent. It's very likely. So it's very likely because why? The uniqueness part says if we only allow this f to be in the special group, then it's unique. But generally speaking, we want some equivalence from the group may not be from special group. So now let's discuss, so how many different representation elements we might have. That depends on the group structure of the manifold. So this is depends on group structure, okay. So now, so let's say for any T1, T2 in the order, the Heisenberg, okay. So the Heisenberg, and we assume T1 is not equal to T2, and let's assume, for example, the order, say M, and the origin is the trivial one. There is no homomorphic group. There is no symmetry. So there is no symmetry. So at the origin. Now this M. So first you can use T1 to map it to M1. So the image. So there's the image. Now we have a normalization. This is the normalize the map. It's normalize the map. Okay, mapped in the normal form. Now this is normal form 1. Normal form, okay? And you can use T2 to map to M2, and then use F2. So this is also in the normalized map. So this is what the field says. That says of M to the 2 normal. Okay. So now if you are here, you can send the normal form. So this happens if only if. So this happens if these are the same, then essentially we say. So then essentially we put back T1 composing F1, F2 inverse, T2 inverse. Then this is going to be automorphism group. So inside here. And we know generally speaking, so this group is trivial. Let's assume it's trivial. Then it implies T1 F1 equals F2 inverse, T2 inverse. This is the identity. Okay? And this would imply that F1, F2 inverse equals to T1 inverse, T2. And we assume these are also satisfy normalization condition. So then this also satisfy normalization condition. Okay? So then we know that for the element in the group, so once you set the normalization condition, then they are the same. So this means.
What is this delta square? You mean the biharmonic? This delta square is the biharmonic?
Oh, the delta? This is the Laplacian.
What is delta square and delta?
Oh, the Laplacian spell. Yeah, this is the Laplacian, okay. So just
That's the biharmonic of.
Yeah. That's the Laplacian, so you probably 4 times or whatever.
Just to make sure.
Yeah. But it's the Laplacian operator. So Laplacian spell, Laplacian cube. So this is the trace condition here. So once we got here, then it's very easy. So then the uniqueness. So any element here, Heisenberg, if you satisfy the normalization condition, like I said last time, normalization condition means so that's just before, okay. So this means this is Z plus high order term, W plus high order term, and the G part, and this is FG. So linearized part, for the second order term, there is one more condition. So then it implies T1 composing T2 is identity. And then T1 equals T2. Then T1 equals T2. So what does this mean? So this means essentially, okay, so this is the generic case. This is the generic case. This is the identity. How many representatives this M has? This M, so how many representatives this M has? So inside this normal form. So this means generically speaking. So generically speaking, So generically speaking, okay. So there exists exactly. So this many. And so representative in a T-model normal form. And it's impossible for you to recognize. So which are two in the same class. So in this sense, the T-model normal form it's not really normal form. It's like pseudo. It's slightly different away from normal form. This makes it very hard to apply in some case. But on the other hand, if in several complex variables, okay, if I give you two specific examples, it's very hard for you to see. But if you want to prove genetic theorem, it's easy. It's not easy. So now look at the T-model normal space. How much you have? So essentially, so this is the T-normal. So it's very large. So these conditions are very tiny conditions. It's only possible.
So when you say generic, is it like some bare category or something?
No. So this means so generic. This means you perturb analytic, then it destroy the symmetry. Okay. And then since you said that, okay. So essentially, the larger this group you have, the less representative element you have. Okay. And in particular, for the highest one, there's only one. Highest one is the only one which has just a unique representation. The more symmetry you have, the better normal form you expect. Okay. And so wherever I want to get an exact normal form, but there's a big Russian school, Vysotsky school, and Webs did a lot of things on this stuff. But so essentially,
you said the more symmetry you have?
Yeah, the more symmetry you have, the less representatives you have in the normal space. So this means you can easily recognize it. Okay. So for example, this Heisenberg has only one. Okay, and you have because this group is the biggest one you could expect. Okay. So now, this is the first remark. The second remark says this is a disadvantage. But on the other hand, if you want to prove a genetic theorem, you allow some perturbation. This theorem is good enough for essentially all the application. So let's give you one example. Okay.
So if the odd zero M is identity, then it is general.
Yeah. So this is generic. It's called the generics hypothesis.
And in other cases, you say generic is.
Generally speaking, it has exactly this many elements.
This odd.
So it's
parameterized by the odd zero M orbits.
Yeah. So it's not exactly obvious. It's impossible to write it out. Yeah. So because you have no control of this map. So T you map it here, so then you get complete different element. But then you normalize it. So for different T, you get different normalization, normal form. That's for sure. Okay. So the second part is that, so now let's look at what we call the space of the normal space. So the normal space NCA. So this is the huge function space. Look. So there's actually so this is it's a unidimensional, so uncountable. Okay. It's a Fresher space actually. Okay. And so now actually for each element, so you at the most have this many representatives. So the portion is still unidimensional. Right? So but this infinity is very big infinity. So in this sense, so the modular space we get the modular space is unidimensional. So hence the modular space is unidimensional. You have the modular space for strongly pseudo-convex, for germs for strongly pseudo-convex hypersurfaces. So it's unidimensional. So it's unidimensional. Okay. Well, this is very different from one-dimensional case. In one-dimensional case, so the modular space is just zero because any real negative curve are the same. They're all the same. You can always flatten it. Okay. let's give you at least one more example. Okay. For example, so let's give a theorem by Braun, Schneider, and Wells. So this is 76, 78, 76, 78, 78. I probably Paul can remind 76, 78. So they put very nice. So for example, he said, so they put this theorem. So a generic small perturbation, smooth, simple smooth small perturbation. Of the ball Bn, so it's still strong, still convex, it's not bicolomorphic to Bn. So this is called the non-Riemann mapping theorem. So it's called a non-Riemann mapping theorem. So there is no Riemann mapping theorem. So you might today, the proof is not hard, but it's still based on Chern-Moser theorem and Fermat theorem. By no means this theorem so it's trivial. It's very deep, but it's what is expected now. But at the time, it's very significant result at the time. Okay. So for example, so I'm just telling you. So what kind of theory you can prove? So you use this Chern-Moser normal form. Okay. So you have two generic. If I really give you two something, it's very hard to. Well, so to make this up, I work with P and Dima, and then we get a nonlinear normal form. It's very practical. However, we have no way. So there's no way for us to prove the convergence because there's no geometry. And in fact, I think it's 96. 96, because I attended a workshop in honor of Professor Chen for something, And Chen told me the story actually, he said when Moser, so essentially all these are considered by Moser, but for this part, but then he made one crucial observation, and Moser got this normal form, and then so it's very hard for Moser to give a convergence proof, and so Chen said, probably you need to use geometry, and he said, so since it's conformal geometry, you should bring in this wire tensor, and that's exactly the right condition, and it fits led essentially convergence proof. And if you, I'm not going to tell you the proof of this result, but this geometry played a fundamental role. And also, I remember these things. Okay, I said, when you want proof of convergence something, you need to try to bring some geometry. And actually, that's later I used in my paper another conjecture. So Moser, okay. So I'm going to tell you tomorrow. Okay. So this tiny little geometry can help you to solve very important problem. Okay. So if you just work on power series, sometimes convergence is very hard.
What quantum is the real quantum?
For this condition, in terms of Chen, he said he proposed this condition to Moser. But all this theory was developed by Moser.
Which tensor is this?
So I'm going to tell you, Chen-Moser wire tensor.
It's not a tensor which Alice said.
No. So this is the wire tensor. It's wire tensor. I did not tell you any tensor yet. I'm going to tell you right now. Okay. So so what I mentioned that this is the geometry. It's called the trace formula. It's called the wire tensor. Okay. And so you import this normalization.
This is the complex analog of Alice's.
No. So
there's no metric here.
Yeah, there's no metric. Why? So So I'm going to define it's conformal value tensor. I'm going to prove it later. Okay. So just be patient a bit. Yeah. Right?
It's called context.
Yeah. So this is the trace condition later. Okay. I'm just going to define this tensor. It's conformally. So it's called. So this tensor actually is Kertano. It is let me see Kertano. Probably not Kertano. It's later. Kertano at the time. But it's very good point. Okay. We have no metric yet. So I just start from here. Okay.
There's no metric, but there's an affine.
Yeah, I can define. I'm going to define tensor. Okay. Yeah. So look, the whole procedure is the crucial point is that so you find the right normalization condition to make it's a normal space. There are zillions of ways to get normal space, but only some normal space fit your properties. Maybe someday you you find some other problem you want to solve, you have to come up with your own normal space. But that would be very nice whenever you test geometric application. So, probably as I said too much. Okay, now I really have to explain to you. So I said, what geometry you need? I have no metric, I have no tensor yet. So everything is formal power series. But now I'm going to tell you something about this. Now there's one more remark. So which has to I have to say. But then people there's one more remark. 3. Which made this procedure works, okay? And so this would be the main motivation for my talk tomorrow, okay? So the crucial thing, so here, the normal space is not hard to achieve. It's a linear operator. It's very simple linear operator, okay? It's L operator. It's not hard. It's just F minus Z times G, okay? So what makes it work? So when you use this operator, you have to pay price. You cannot use the whole group to normalize manifold. You want to use this group here. So, no, you want to use normalized map to get the uniqueness of the L operator, okay? Right? But in some case, so you left out this group. You left out, essentially. So, this is the whole group. And then you use a normalized group. And this is when you left out this element. You left out this tensor. But in many other situations, you are very lucky here. In many other situations, this group could be infinite dimensional. This group could be as large as your normal space. But then you cannot be essential. You cannot, so then this normal point is totally useless, okay? So you cannot do it for anything. This could be the case. This happens in many problems in cellular mechanics. So that's why it's so hard to get very nice normal form there. We solve a lot of and also this happens when you normalize CR manifolds with CR singularity. But in this case, you really need to find a different normalization. So far as I know, there are two. So tomorrow I'm going to introduce here. If this group is sorry, it's the model. It's the model. Okay. This group is finite. Okay. So if this happens, if this is unidimensional and as large as the normal space we get, then anything could happen. Okay, anything could happen. But then we have here essentially there is a theory by Morton-Webster. But in this theory, there's theory in SCV by Morton-Webster that I'm going to introduce tomorrow. Okay. And also, there's another method developed in my recent journal with Yin, with my former student Yin. Okay, I'm going to talk about this tomorrow. Okay. But now I'm going to answer your question. Okay, so so you asked what tensor we are going to. Now I'm going to get into sections. It's only section 3. Yeah, mono wire tensor. So mono wire tensor.
It is the same as the Cartan tensor?
No, actually, there's some connection, but it's not the same. So you have a metric, you have a culture, then there's a wire tensor, right? But here, we have no metric. But actually, Webster later wrote that paper, actually support you, the big exponent, okay? And Sargon, we have a lot of expert here. And the Webster wrote that paper. He introduced the pseudo-Hermitian metric. And then he said you cannot use the same formula for his metric to produce his tensor. Okay, that's the major motivation for him to write that paper, because he wants to compute the Chen wire tensor using effective way. Okay, Chung-Wire tensor, but that Chung-Wire tensor was there long before Webster started working on this stuff. Okay, so I'm going to tell you from the very beginning how people define this tensor. I think probably Tertullian at his time, I'm not sure Tertullian, but at least Tremollas, they define this. Okay, Webster was still a trend. Probably, that's a. So now, the tensor I'm going to tell you is actually from the origin, how it's defined. The original is defined. Okay. So first, let's prove a lemma. So prove a lemma, okay. So this lemma make up essentially the proof of Tremollas. So the Tremollas normal space, I said this normal space, I did not give you proof. But actually, so the proof is on top. It's more or less like this kind of type, okay. For any real value. So polynomial value equal 4. So essentially there exists. Yeah, it has to be unique, So I think so. There is a unique holomorphic function degree 3, degree 4 holomorphic satisfied normalization condition such that L F3 G4 is going to be P4. It's not solvable, okay? This may not be solvable. I said if it's solvable, there is no force working value. However, you can make up by adding some other term, then it's going to be solvable. So what are the condition on L4? Such that this is equal to, so with N4 equal to A alpha delta, B alpha, B alpha equal to 2. And then the Laplacian, the delta Laplacian N4. The trace condition. And so moreover, so this N4 in the bar is unique. Okay, so I have to start from here. Okay, so it's unique. Let me see how much time. So the proof is just one page. Okay. So let's give a proof. Anyhow, we did not do a lot of proof. So let's give a proof. This is contained in the Tremollas normal space, but anyhow, I did not prove anything there, so let's prove that. For the other situation, the proof is similar, but it's slightly more complicated. So it's formal policy argument, essentially. So first, let me write this operator. This operator is a very simple operator. Okay. So this is a real polynomial. This is a real polynomial. Yeah, real polynomial. So we can write like this. Because this equation is restricted to this space. Okay. So let's simplify it. This can be written as like this. You can further written like imaginary part A4 Z plus B2 Z. I replace U by W, then I get something more. Right? So this is a B2 non-dispel plus B0, etc. I do all this. So I replace U by W minus I non-dispel, and then I let G4 equal to A force Z plus B2Z W plus B0 W square. And 2 minus 2I F3 J DW CJ z minus I d2 dbj minus 2I djw. So, this is the first one, and as I let this, okay, and then so then if I suppose solve this like this way, it's not a solution. Let's look at the difference. So if I do this, so then, so what I get is tilde of 3, t force 3, I minus p4, then I just answer like this. So I cancel all non-needed term except this one. This one I cannot cancel here. So I can cancel all the other stuff. Okay. Now, so I want to solve this equation. I want to solve this equation. If I can solve this equation, then I just put it in. Because it's a linear space, okay? So I want to solve this equation. And this equation, I want to solve this equation, okay? Now let's solve this equation. And then you do Taylor expansion, you find the only possible way to get to solve this equation is to take F3 equal to P1 dW. So this is solved if and only if F can take this form. Okay. And here there is a more condition here, the real part. Z bar P1 equal to 0. Okay. And you plug it in, you want one more condition here. 2 Z bar P1 Z non Z squared equals F1 y. So this is going to be d alpha delta bar, d alpha d delta bar. Yeah. So this means that this is only solvable. So when F take this form, okay. But now I do the Fisher decomposition. So Fisher decomposition. This means any polynomial you can write something like h11 non-z squared and plus harmonic function. Harmonic function. This is a harmonic function. Yeah, it has to be two times harmonic. So there's a unique decomposition. Okay. And then so you see here, so then you see that because the Fisher decomposition is unique. So we see that we see that this part has to match up with this part. So this means essentially 2z bar p1 z. You will cancel this one. So this one, so you can so this one has to equal to this one. So this is solved if and only if this guy equal to 0. This is the only condition the only way you solve like this. So the only way to solve it. Well, if this is given, if this is not equal to 0, then there is no way you can solve this equation. However, I can only choose P1 to make this guy equal to 0. So this means that this term stays in normal space. Okay? So what I'm saying is the best way you can simplify that, you can, the best way to simplify that, so you can make this term completely harmonic. Not divided by normal squared. So this is actually, so this is one, so why it's unique? The unique is obvious because it's down here. If there are two solutions, they are given by the difference harmonic function, which is divided by normal squared. But then the Fisher decomposition says they have to be the same. So so this is how we prove this.
What exactly is Fisher decomposition?
It's called a Fisher decomposition. It's harmonic. So this people use in spherical harmonic, right? Yeah. So
it's a spherical harmonic thing.
It's SO1 or
so it's a Fisher in no, so it's like this. Okay. Decomposition. It's slightly more general than that. It's something like so essentially it says for any polynomial, degree say is for any polynomial you can decompose it into something divided by something like this.
A real valued polynomial.
Yeah, real or I don't know. So if it's not real, you just write the imaginary part real part, and the map is the same, right? So it's P1. And this one is harmonic. This is an inaccurate and sovereign. Yeah. So you can choose any like a project polynomial, right? Or even higher. Yeah. So any project, any polynomial put here, you can do this decomposition. But this one is inaccurate by the operator defined in this way. So in this situation, then P2 is harmonic. So this decomposition is unique. So this is how you get the normal form, normal space. So, so now I'm going to answer your question, okay? So at least by now, so we see this M can be defined by notice square M4 ZZ bar. I did not prove the model theory, okay? Theorem, okay? But what I proved by now, I said that there's no event for degree 3, now there's an event degree 4. This one, there's no way you can. But the only thing I can make is this one is harmonic, plus high order. And in fact, as Paul last, so when you highlight it, now that's good enough. If you work not just on one point, any other point nearby, that's good enough to determine the geometry. So this M4 has this property, the Laplacian M4 equal to 0. Okay? So this M4, let me write like this. So let me write like this. It's a pi degree 2, 2, so we can write like this. So of course, if you want this decomposition to be unique, so you need this symmetry. This is basic symmetry. Okay, so here I have no matrix, but I can still define a tensor. And the reality condition, of course, reality condition. And the reality condition, this is going to be S delta alpha bar delta gamma. And then plus this condition here. Laplacian M4. Now let's write what this condition looks like. This is exactly the trace condition. It's a very important geometric condition. So the trace condition, so let me see, this Laplacian M4 is exactly summation G delta bar alpha S alpha delta gamma delta. Now I write it in the tensor form, okay? So what is a G alpha delta bar? That in our situation is just alpha delta. Okay? And then, so this means summation with respect to alpha delta. And this is and G alpha is just minus. This meant, okay? Yeah. So Laplacian, so hence we have this condition, the trace condition. So these are curvature property, okay? So curvature tensor property, and this is the trace condition. And because you put them together, you call this the, so you put
But what is the G you're using? Just
the G right now, so in our normal form, it's just identity, it's a level form with respect to this, it's identity now. Identity matrix.
yeah, that's
Yeah. In our situation here. But now I want to generalize, okay? Yeah, but then I need to do something a little bit more, okay? I don't know, so if so I have to repeat a lot of stuff. Yeah. I prepared a lot more, but then I so if I so this is so let me give a definition. So now let's define the tensor, okay? Now so yeah, let's do slowly, okay? Whatever, so now let's start from some scratch, okay? Now what is Chern wire? So a lot of people talk about Chern model wire tensor. Actually this is the origin of this tensor. So but then so how is related to the wire tensor in the Riemann geometry? That's the work of Webster later, okay? But I tell you this later, okay? There's a connection. But right now, there's no geometry. It's all from the Taylor expansion. But we know the curvature from the Taylor expansion of the metric tensor. It's also surprising in some sense. So now, we start a manifold M. Oh, let me say a few words. Here, so even it's dimension 2, this is identical 0. Why? Dimension 2, dimension 2, dimension 2, there's a dimension 2, this is identical 0. There's only one index, right? This is 1, then this is identical 0. So then you don't have any fourth order term. Okay? You go to fifth, you find fifth, it's all 0. And sixth is start get a tensor, non-trivial tensor. It's called Capron tensor, Q tensor. Yeah. I don't know if the Q tensor is related to your Penrose operator. It should be. The Capron Q sixth order tensor. It should be computable, through the Penrose operator, right? To relate, no? It's not in that sense.
Well, that's interesting. You can't touch it.
You can touch it, yeah. But
It's related to the Bose-Einstein.
huh? Bose-Einstein, okay.
If you make the variation.
But so here, so to make sense of this part, we have the same answer. So at least in C3, in this space. Otherwise, so there's no that. So it's a different story, okay. But that part is, in some sense, you could say it's simple, but then on the other hand, it's harder to use because you don't have more differentiation or differentiation. So now let's say something, okay. So first you have any point P in M. Yeah, so you need the minimum contact form. And P is contact form. P, so Paul talked about this. I'm not going to repeat. This means essentially this annihilates. This annihilates, so the and basically, so non-degeneracy annihilates this space. And so this is not equal to 0, of course. In strong single convex case, so in the embedded case, this is enough to say. So for example, if n is defined by I equal to 0, and the assertion with this defining function, you can define theta is minus I dr operator. So then this is contact form. It has to be real form. So real form, okay. So why is real? It's very simple because dr restricts to n equal to 0. That's why it's defining function.
I think we need a d bar also.
Uh-huh.
In your definition of theta, you have to subtract dr minus d bar r.
You mean this one?
Yeah.
No, there's no need. So this is real, okay. So dr is a dr plus d bar. So this is the imaginary part, right? Yeah, you can write it, it's okay. Then you divide by 2, this is the same. So this means theta bar equal to I d bar r. Okay, then it's okay. So it's a real value, okay. I restrict to the same. You're right. So, but you can write d bar, but they are the same. They're given by negative sign.
Oh.
Yeah. Okay. But then, so this is the contact form. Okay. Now, for any xp say yp in tp10, and for any contact form, we can define the Levy form. So let's do that. So let me not do it in the back channel notion. So then the contact force, the Levy form associated with this, you exactly define the Levy form at P. So this is the Levy form at P. So the Levy form at P, okay. So this is called the Levy form at P. And then we always in a strong single convex case, we always assume this form to be passive definitely. If M has a signature, we want the signature to be bounded by half of the image. M is something like this, okay. And then you have too many content form, okay. You have another content form, right? So then the Levy form is defined exactly C times. You can just multiply it, okay. So you have this Levy form. Now let's define the Kermode wire tensor. Now, so far I did not mention anything here. Now assume that M is a Levy non-degenerate. So say strong single convex of signature L. L bigger than 0, okay? So this means when L is a strong pseudo convex, and we let's say theta P be a content form of M at P. Of M at P. So, and we know that, so suppose F is a biholomorphic map. So this maps P to M tilde, P is mapped to 0. This is map, so P map to 0 such that M tutor here is defined by in a Tremolta normal form up to 4th order. So B equal to norm spell. Let's assume L equal to 0, okay? Minus 1/4. And this is the small, so big O5, let's say. And then so we know that so this theta, suppose this theta, you push forward. Here there's a defining function, and there's a you push this one, so minus I P R0. You put this back at the origin to suppose this is CP. Because two content can only be given by constant C. Okay, so then any XP, YP, DP, WP, this is inside this space. So this XP say be written as so A. So let me see AJ EBZJ YP equal to BJ EBZJ ZP equal to CJ EBZJ and WP equal to DJ EBZJ and all restrict to P, okay? So then the model Y tensor with respect to this content form is dependent on the content form, okay? So XP, YP bar, ZP, WP bar. So this is defined as, so you have to divide by 1 over C, the summation of this tensor. So that's essentially alpha delta gamma delta bar, A alpha G delta bar times C gamma T delta bar. So that's how you define the Y tensor. So why you put my one C here? But now there's an invariant property. So too much right here. So you push it to the standard defining equation, right? And then this is the Y tensor in the standard defining function. And then so when you push it, your content form may not be like this one. So then you have to correct that term, okay? And once you have this, it's not easy. It's not hard to prove. Then there is a theorem, transformation law. So the theorem says, this is M, strong pseudo convex. So you have a content form at P, and suppose you have a biholomorphic map, F tutor. So another content form say at Q, and assume that so F sigma P Q tutor, you pull it back, is exactly sigma P. Suppose that. So then for any XP, so not just write XP. So the other one you complexify, then you get a general phenomenon M. So the Y tensor is exactly SQ filter. We push forward XP and we push forward XP. So you have this invariant transformation formula, okay? So I only have about 15 minutes, okay? Now, so this is the definition of the model Y tensor. Well, let me give some remarks. So more or less, so this tensor determines the complex structure of M, but in a very complicated way. It's not very simple. And so how is this decided? You have to use, you have really to use the geometric part of the model field to see that. But if for the formal partial part is not enough, you really have to go to higher order. Okay, so for any point, now you fix the complex form. For any point, there is a Y tensor. For any point, there is a Y tensor. You really have to connect all of them to see the geometry. If you only focus on the one point, then you really have to look at the higher order invariants. So that part, so I did not divide here. So that's essentially the differentiation of this tensor with respect to some special connection. So this is the second. So how is related to geometry? So the truth. So how is related to the classical Y tensor? So this is the work of Webster. Okay, and so Webster did. Paul talked about a lot about the pseudo-Hermitian metric. Okay, and there's a formula by Webster. Okay. You fix the contact form. Let me write this Webster formula. So let me write Webster formula. Okay. So you start from a contact form, then you can derive essentially. You can have like a pseudo-Hermitian connection as a metric or whatever. Okay. And then you have a Webster Tanaka coverage tensor. Okay. And then there's a suppose we write this R delta and delta. This is the Webster coverage tensor. So this is the coverage tensor. Well, it's more or less related to the coverage tensor from the Riemann geometry, but it's not exactly the same. So then. So we have this formula. It's called the Webster curves. So we have this formula. So the formula says F alpha delta gamma delta. So with respect to this, so this F with respect to theta, we all fix some theta. So this can be done by this. So essentially, so their difference is conformally flat. So what I'm saying, the difference is actually so much of the metric tensor equal to 0. So everything is related to the metric tensor. So if it's if I have more time, I would be happy to explain the whole thing in the book. So we have to skip a lot of stuff. Exactly, yeah, you're right, exactly, yeah. So anyhow, so what is the crucial issue is that the difference is 0 modulo the metric tensor.
So it's like the Riemannian case, no?
Trace free.
Yeah, trace free, yeah, that's exactly, yeah.
Except for the constant.
Yeah, exactly the same, yeah. So here's the issue, okay. From the way that the model Y tensor is defined, it's not clear. But then, so I think so that the thesis, the Chen guessed, they should be similar to what happened in the classic geometry. And that's the motivation for Webster wrote that paper. And eventually he wanted to do this. So that's how it was, okay?
You do have the minus in the second one.
Minus, I think it's plus minus. I think it's plus, right? Plus, yeah.
Which one?
Second.
It's possible.
Or the second, yeah, it should.
It should be like it's a sum, right? I mean, from the full Riemann tensor, it's like
No, why is minus? It's a plus.
plus scalar curvature. So it should looks like minus. Right?
A weight with T.
So okay, just like
Yeah, so
I
what
think the difference is really discounted.
it's cardinal, right?
That's shortened tensor.
Yeah. So it's plus, okay.
It's a column.
Yeah, it's plus.
Well, I think it's the second line.
He's bothered about the plus R. Is that
You plus or minus R, right?
No,
This is
about L gamma.
No, R is minus, okay.
I
The
write
second.
You mean this one?
I am
Oh, here, you mean so here, so this is like this.
That's the bracket. That's the whole
It's bracket, okay.
also, yeah, that should
The
be.
1 over n plus 2 is going to be the
No,
whole
but-
bracket.
You know, so don't worry, okay? I can use this for many things. It has to be correct.
The original is correct. Don't.
Yeah, this is the original. This is here.
The first bracket ends in the first line.
The first bracket and the first line, what do you mean?
The original formula is correct. Don't change it.
This is.
the corner of the first line?
Yeah, I think that's the right one. You know, so so this is correct. Okay. So let me see here. I can check the maybe here. Okay. So this is correct. So then, yeah. So what I wrote is correct. Okay. Like that. Yeah. You think this is that is?
Yeah, I thought that is minus.
No, of course no. So you know that should be symmetric. Why it has to be minus? It's minus. There is not matrix, right? It's not symmetric. There is no symmetric property. So why delta is different? Why gamma delta index should be different? There is no symmetry there. So you think about it. So there should be so this should be so symmetric. Okay.
So this S alpha beta is a tensor, is trace free.
Oh yeah. It's pretty good. Yeah, you can do the trace. Okay. So this means you collect this. You know. So now this is a Levy form. You know. So alpha delta is a Levy form. It's a L theta. It's a Levy form, and so this is the inverse. So so this alpha delta now is still a Levy form. So I only have 5, so I don't have so I have to skip a lot of stuff. You know, I computed many times. It's correct. Okay. You do the trace free. You find it. So why it has been active? They should be symmetric. Okay. So here, the crucial issue for application many times is so this method, why it's so useful? People use this in doing cell transfer because so this is the invariant tensor in some sense. But these tensors they are only given by a metric tensor. It's called conformally. So so there are a lot of there's a Caton is what the Caton Keller manifold. In Keller geometry, if the curvature tensor so it's conformally flat, this means this time equals 0. It's the Caton. So essentially everything you see our geometry, you can do it in the Caton Keller geometry. And so we talk about Robert Bryan. He wrote many papers on this, and a very important paper. He had a very long paper on the classification. But anything, his paper is modified to model tensor. So this is a very important tensor. Now, so I mentioned several things. So for example, let me give us give some from here. You see, so normally speaking, so this one is very difficult to compute. This tensor is very difficult to compute, although it's fourth order. But when you really want normalized defining function, at the second order you start using implicit function theory. You use 3 or 4 times, but then eventually it's uncomputable. Okay, and now so this formula give you a very good thing. Essentially to get this tensor, you need only differentiate the defining function. So here is more direct way to do it. So here the curvature tensor, metric tensor is all from defining function. You just differentiate it many times. So this is the very direct way. So that makes this formula is extremely useful for computing the trivial things, make it computable. And actually, so you look at the paper Webster, and actually, so Webster told me many times. Okay. One of the major operations is so for him write the paper is compute this one, in particular to compute the ellipsoid. So for sphere, it's 0. If you go beyond the sphere's ellipsoid, even for ellipsoid, it's impossible to compute this one. Okay. So with this one, he could do it. In the last section of this paper, he started to compute these things. Okay. So this formula, but of course, then people found a lot of other applications. That's his original motivation. So now there's another way to see that. So from the definition of so this tensor, you couldn't see much. It's just defined at a general level. But now actually you see there's really behavior. For example, you can define, so for example, you have a smooth vector field x, y, so a. So as a smooth, you do any smooth content form, you see, so this one is as regular as x, theta, and the manifolds. So this is also this means you can differentiate the term y tensor. It's useful for you to further produce other invariants. So this is the general philosophy. But now, so what I want to say, there's a lot of place people use this fundamentally. So the next place, so there's another lemma. It's called I would say the theorem. It's one of the very important theorems, Canonical theorem. So unfortunately, you want to prove it, you have to use it. You cannot do it by using normal form yet. But this means if this tensor is identity, then if and only if M is spheric. So this means CI equivalent to the sphere, with Heisenberg, never said. For this one, so you have to go to the Haung3 model theory. You find, that's my purpose to talk about the Haung3 model the next time, but I thought I'd skip it, okay. So now, let me at least mention another case of data conjecture it's a very famous conjecture. It should be related. So you might know there are a lot of connections with many other famous conjectures in the field. Okay. Let me at least mention these what they call. So this is one of the very famous conjectures in the subject. You call that Ramadano. So anyhow, so he was in the crowd, but then he so 70s, 70s. It's already appeared under 78, 70. Okay, yeah. So we know that. So if you have looked at strong silicon instrument, strong silicon wet. Infinity bound is strong silicon wet. And so you look at then the Boltzmann function. The Boltzmann function has an asymptotic expansion. Rho. So rho is the defining function. And then here what you know is that this is infinity smooth up to the function. Okay. So what about the conjecture? Okay. So the conjecture says, so the conjecture says D is spheric. If and only this psi Z vanishes in below at the function. So I will have this problem. Okay, so this psi Z, the value is invariant. Okay, so so the Boltzmann kernel. Yeah, for stick kernel probably there's some similar conjecture. So this part. So this part follows from Feynman. Feynman already know that. Okay, it's actually Schott and Putman well. They derive this. Yeah. So as I mentioned before, the higher contact all you know about the sphere, the better asymptotic behavior you get. Okay. If it's a sphere completely asymptotic, then you can prove that. So this part is no. This part is this part. This part is okay, and this part is not. And there will be a lot of work trying to figure out how this function is connected to this distance, okay? And so, unfortunately, I won't be able to do that, okay? And so, dimension 2, and 2 itself The sound if I put them on where? And then so brand. Okay, so it's sound. Even 2 is okay. High dimension, I think he wrote right, wrote a lot of paper on this. But still, you know.
So, I think you're talking about a stable kernel.
No, Boltzmann kernel. It's it's called yeah. So it's called Ramadanov. Okay, so he's guy working on Boltzmann kernel.
And I don't think that's what we take solve.
No. It's not sound dimension 2. Sound dimension 2.
So O equal to 2 is complex dimension 2.
Complex dimension 2, yeah. So C2 then is sound.
But I think we take solve the stable kernel, not the kernel.
But so at least Prof Schneider, you know, so but they sound. So this is in the preceding paper. So yeah, I can use the reference. So I can use the reference. So for sure in this paper you can see equal to 2. But anyhow, dimension 2 is answered. Okay. There's single tangent.
Also, the expansion, the first term should be minus n minus 1. No?
Oh.
Okay.
Fancy. Yeah. Okay. Yeah.
Otherwise, it doesn't.
So this is for Boltzmann kernel. It's one of the very important problems in the subject. Okay. It's one something which does solve. I think so the best way now. So this needs a lot of computation. About psi G, how you connect this with the Chamorro wire tensor. So how you compute them? You know, it's a very hard problem. There's some connections. Okay. So this is the second thing. Now the third remark I want to make. So this is actually what I intended to talk about before. You know. So probably it's 1 more minute I'll be done. Okay. Now let me make one more remark. So I'll be happy to send to you what I wrote about this. You know, so there's another survey paper. It's not appeared yet. It's a very long survey. So it's not survey. It's kind of a summarization of the. There's another thing. Okay. So look at this. Look at this tensor. It's a harmonic function. It's a very bad function in some sense. It has no sign unless it's 0. Right? It's no sign. Okay. Well, once it's no sign, it's not really like behave like a code. Okay. However, so there's an observation made by me and my student Yan Zhang. 2008. So we are in a special invited paper for chance. We noticed that actually, if you go to very non-degenerate with positive signature, this part then the trace condition is a wave equation. The trace is a wave equation. Wave equation could have a positive solution. Yeah. Then this guy behaves very much like a curvature function. It's a true curvature function. And we found a lot of application actually. So this is the so all you know is this guy is 0. But this is a solution wave equation, not too bad. It has a sign. And we have the positive problem. So essentially, so for example, if you have a map, I don't have time. Okay. You have a map. So if you have a map, essentially the curvature, so the wire tensor decreasing. So it's more like a homomorphic section curvature, but only along the null space of the Levy cone. And from that, we have a lot of applications, including many examples, which are not embeddable in any models in any dimension. So what I'm saying that so for this tensor, it's still this is a very mysterious tensor, and so our knowledge is very limited. Theoretically, so it's there.
Where is this paper? If this is
so yeah, I can share the paper. So let me tell you. Yeah, it's 208. So it's 208. So I can give it. If you come to my website, you can find everything about it. Monotonicity about the wire tensor. Okay. So what I'm saying for positive signature, but for strong silicon wires, it's unfortunate there is no some problem because it's harmonic function. There is no sign condition. You cannot assign any sign there. Right? So it's a science in China. It's a special issue in honor of Professor Johnson. And so there's a monotonicity. And so this case, once you know a little bit problem, you can go a lot further. There are many. So for example, we solve the long-standing open question there. But just make an observation of this monotonicity. It's about non-eventability for the output case. I think so far I should stop here. So my plan is, so actually, I prepare to talk about geometric accounting model. Probably I should stop there. Okay. So you can, in my lecture notes. So next time I tell you something about CR single space. Yeah. Now, so this is about Boltzmann kernel. About Boltzmann kernel. Yeah. So you can put the is also possible. Because they can decide. It's not possible. I think